Hi, Algebra 2 honors students. I know I will not be as fast or nearly as exciting as Mrs. Crowfoot, but I'm going to give it my best shot today in getting through Unit 16, Day 1, some quick information about identities for you guys. So the identities that we're going to learn this year, there's going to be a lot more of them. We actually know some already. So for example, the fact that you know that cosecant is 1 over sine x, that's actually an identity. And that identity is something that we'll use to eventually, in this unit, prove that certain things are true. So we'll get into that part in just a little bit. But if you look at the filled-in version of the notes, there's this big copy of the unit circle drawn in the notes for you. And I tried to recreate it with a plate on my page here. And I'm guessing maybe you can't see this full image, but I traced the unit circle. I tried to pick where the center of that circle would be. And if you take a look at the triangle that I've created, if we're dealing with specifically the unit circle, I'm hoping that you remember that the unit circle has a radius of length 1 unit. Okay, so when I drew this radius to this point xy on the outside, that is 1 unit there. And the way that we actually develop a lot of what we've done so far with trig is by knowing that if I do cos of theta and sine of theta, well, since sine is opposite over hypotenuse, we would have that sine is actually equivalent to the y value. So the y value would be this height right here. This side of the triangle could be expressed as sine theta right there. And we know that cos theta is equivalent to the x value there, right? Adjacent over hypotenuse. So since cosine is adjacent over hypotenuse, adjacent's that side that we call x. Instead of calling this x, I'm actually going to express this length as the length of cosine of angle theta. And once I have that filled in there, we're going to get to 3 new identities for the first time today. And looking at this right triangle, I'm hoping one idea that jumps out to you is that when we have right triangles, we can do something called the Pythagorean theorem. So what I'm going to write down are some Pythagorean identities that, again, are listed in the notes, but without having any explanation, I think it would be probably a little bit confusing to understand where all that was coming from. So if I look at this triangle, if we have a squared plus b squared equals c squared, well, in my case, that's going to be that sine squared plus cosine squared is equal to 1 squared. And instead of writing 1 squared, I'm just going to say that, hey, 1 squared is 1. So that is one of the pretty major Pythagorean identities that will come up most frequently in some of our work. Okay. Now, some of the other derivations for the other ideas there is if you look, there's a triangle in the notes somewhere where, hey, if this radius is 1, then if I went straight up to the top of the circle, that would be a radius of 1 unit. And if you kind of copy that over, I'm going to extend out this hypotenuse pretty far here. Okay. So if I extend out from the top of the circle, okay, I want to copy over that length of 1 right here. I'm going to actually create the length of 1. I'm sorry, we're going to intersect sine theta there, but I'm going to create this length of 1 going on the opposite side of theta. Okay. So if I now define this kind of purplish triangle here, and copy over this, such that the opposite side of the triangle has a length equivalent to 1 unit here. And again, I was able to copy that because this is another radius of the circle, so kind of just copying that distance over there. You know, which of our ratios depend on the opposite side in the denominator? I'm hoping that the ones like cosecant are going to stand out to you. Cosecant would be hypotenuse over opposite. So if I take the hypotenuse of theta and I divide by the opposite of theta, that would be the ratio for cosecant there. So this whole hypotenuse can actually be expressed as cosecant. The other one that would depend on the opposite in the denominator there is if we have cotangent. Cotangent's adjacent over opposite, right? So if I do the adjacent side divided by the opposite of 1, we can actually express this length as cotangent theta. And once I have that relationship, I can use some Pythagorean theorem to get our second Pythagorean identity. So in this case, we would have 1 plus cotangent squared equals cosecant squared. And if you're like, hey, wait, I really want a fun way to remember this, don't worry, it's coming, okay? All right, finally, the last of our Pythagorean identities. Number 3 is going to come from not taking the radius up to the top of 1, but what if I extend the radius all the way out here till we hit the circle? And I say, hey, that's a length of 1, right? So if that's a length of 1, sorry guys, I have a feeling this is going to go off the page here. I'll do my best. But if I extend this all the way up, what I want to come up with is a relationship for, oh man, I just missed it. Tried my best. You get the idea. That would make a triangle, right? All right, so if this whole thing, get ready for it, has a length of 1 unit, okay, which are the ones that depend on the adjacent being in the denominator? The two functions that depend on the adjacent in the denominator would be tangent. Tan is opposite over adjacent, so that means that the opposite side of this triangle is tan theta. And then the other one's secant, right? Secant would be hypotenuse over adjacent. So therefore, the entire hypotenuse here, oh boy, it's all the way up there, can be expressed as secant of theta. And that picture definitely starts to get a little busy looking, okay? But if I come down and write the last relationship here, given these 3 sides in the right triangle, you would get the final Pythagorean identity that 1 plus tangent squared is equal to secant squared. So back to those tricks to remember these. They're tricks that students learn them in Algebra 2 honors, and they really do use them all throughout pre-calc and calculus, I promise. They are good ways to remember these ideas here. So for the first one, sine squared plus cosine squared equals 1. Not my favorite of the tricks, but we'll go with it. I'll say that sines cost $1. And hey, if that's a way for you to remember sine squared plus cosine squared equals 1, then go with it. Sines cost $1. Sine squared plus cosine squared is 1. All right, what's going for 1 plus cotangent squared equals cosecant squared? Well, hey, how about 1 cot is cozy? That's the phrase we typically use to remember 1 plus cotangent squared is cosecant squared. And finally, 1 plus tan squared is secant squared. My favorite, 1 tan is secret. And I'll tell you, I went tanning once in my life, and boy, do I wish I would have been able to keep it a secret. Very embarrassing. It's a story for another time, though. Okay, these are our 3 Pythagorean identities. Now, if you didn't love this derivation, I think we're probably on board with sine squared plus cosine squared equals 1. That one, I think, definitely should make sense to us. We know that sine is y, cosine's x in the unit circle. Like, that's definitely one that I'm thinking we're pretty solid with. Let me just show you a really quick another way to develop those same identities. If you start with sine squared plus cosine squared equals 1, what I want you to do is take that whole thing and divide by sine squared. So that means divide this by sine squared, this, and this. And I want you to tell me what the result of that would be. Okay. So sine squared over sine squared, that's just 1, right? I'm going to jump to this side where I have 1 over sine squared because that's a little bit easier, I think. 1 over sine is cosecant. So 1 over sine squared is cosecant squared. And I'm hoping you remember that based on our unit circle business, that cosine over sine, that ratio is actually cotangent. Cosine over sine is cotangent, so this would become cotangent squared. 1 cot is cozy. Okay, that is one of the other Pythagorean identities. So you can actually take this whole thing, divide everything by sine squared, and get another Pythagorean identity. So then if I don't divide by sine squared, what if I divide by cosine squared? If you're a really good guesser, you'll know what happens when I divide everything by cosine squared. All right, sine squared over cosine squared is tan squared. Sine over cos is tan. Cos over cos is 1. 1 over cos squared is secant squared. So we get tanning once, or 1 tan, doesn't really matter, right, is a secret. And that is the other identity. So you can develop the other two based on that unit circle concept, or based on dividing through by sine squared or dividing through by cosine squared. Just a quick thought there. One thing I want you to start getting used to as well in this unit is that sometimes it won't always say sine squared plus cosine squared equals 1. You're going to see a lot of things in some identity proofs that we'll get to today that might say something like 1 minus cos squared. I'd expect you to know that that is the same thing as sine squared. It's just rearranging this identity right here. If I said, hey, let's get sine squared alone, what would that equal? 1 minus cos squared, if I subtract it over. Similarly, if I said, hey, what's 1 minus sine squared? That would equal cosine squared. So these two, I would say, come up just as frequently as sine squared plus cosine squared equals 1. And believe it or not, at this point, you know, if I add them up quickly, 8 identities. I'm not going to rewrite the 3 Pythagorean ones, but the other 5 that you know what are called the reciprocal identities, because we've actually used them a bunch already today. The reciprocals are cosecant is 1 over sine. Secant is 1 over cos. And then cotangent is 1 over tan. Okay, so we definitely know all those reciprocal identities there. And the other 2 that we know have the fancy name of the quotient identities. If you think about what quotient implies that we're dividing here, right? So what that would imply is that tan is the quotient sine divided by cosine, and that cotangent, we just did this up above here, right, would be the ratio of cosine over sine. So just some other quick identities that we'll be using pretty frequently in some of our practice today. Okay, so we've got 8 identities that we're now going to go ahead and take a look at. How do those apply when we go to start proving some trig identities? So I'll show you what this means. So the first example we'll take a look at is cos theta times tan theta equals sine theta. As a quick note, we've done identity proving in the past. So for example, we've proven something even as simple as saying like x squared minus y squared equals x plus y times x minus y. That's just the difference of perfect squares identity, right? How would I prove that? Well, I'd probably multiply those 2 things together and show that when I simplify, I get x squared minus y squared. Whether you do box method or FOIL, completely up to you, but we can very easily prove that these 2 things are in fact equal. Now, when it says to prove an identity, one thing that I'll tell you is that this equals is really a question mark right now. We don't know that these 2 things are in fact equal. So what that means is that, and I believe we've done this before, I'm going to draw a line that kind of divides the 2 sides of the equals here, and I don't want to cross the line. I can't divide both sides by the same thing. I can't multiply both sides by the same thing like I traditionally would in an equation. Okay, so there's a big difference between proving an identity, which is what we're doing right now, and solving an equation. And solving equations, we'll actually come back to that tomorrow. So what I'm actually going to do is I'm going to come to the left side and remind myself that tangent is really the same thing as sine over cos. So I'm multiplying these 2 things together. If I replace tan with the quotient identity, sine over cos, look what really quickly happens. Cos is in the numerator here and in the denominator here. So you can do that cross-canceling when you're multiplying fractions, and I'm left with sine theta. Well, hey, what's on the other side? Sine theta. So I never had to cross the equal sign to make that happen, but proving identities, you're going to work down one side or both sides if needed to show that those 2 things are equal. The next example in the notes is sine theta minus cos theta, all divided by cos, equals tan theta minus 1. I'll tell you, it might be tempting for you guys to say, you know what, let's multiply both sides by cos theta. I don't like that we're dividing by it. Let's multiply it, both sides. In an identity proof, you're not allowed to do that. Okay, so again, this equals sign is really kind of a big question mark right now. We don't know yet that these 2 things are equal. It's our job to prove that. So in terms of simplifying, I'll tell you, you can really work down either side and still come up with the same results in the end. I'll show you just some of the algebra things that we'll have to start getting used to. If you have a binomial on top and a monomial on the bottom, you are certainly allowed to split that fraction up. And that's probably the fastest way to do this. Whenever you do an algebra a step in these identity proofs, make sure that it makes sense and that it's legal math. I mean, if I subtract these again, would I get back to what I had up here? And the answer is yes, they have the same denominator. Therefore, the numerator would be sine minus cos. But if I separate it in this form, hey, sine over cos is tan. We just did that a second ago in the reverse direction. We changed tan into sine over cos. And then cos over cos is 1. And that's exactly what I have on the other side. So I can just check that off and say, yep, I've confirmed that these two quantities are equal. You know, when in doubt, it's really nice that I know what it should equal. So if you're looking at like tan, oh yeah, I know that sine over cos, it might give you the hint on this side that maybe if we separate some things, we'll get that to appear. All right, the two that are next in the notes say that they're homework, but you know what, I'll do them anyway, just to make sure that we get a little bit of practice in here. So we want to prove that this right here is equal to cosine squared. I'm probably going to leave the cosine squared alone for a little while on that side and really just work on simplifying this side right here. If on this side you distribute sine theta across, you're allowed to do that. So you get sine times cosecant theta minus, well, sine times sine, I'm hoping that you're remembering that that would be sine squared theta, and we saw that notation with equations in the last unit. Sine times cosecant, what would that be? Well, sine times cosecant, they're reciprocals. So when you multiply something by its reciprocal, you should get 1. If you don't remember that, what happens if you change cosecant into 1 over sine theta? Well, you're going to see really quick here that, yeah, those signs cancel, and you get 1 minus sine squared. Huh, man, I really wish 1 minus sine squared was cosine squared. That would be so convenient because then we'd be done. Oh, wait, it is. This is cosine squared. Done. I mean, whatever you want to put over here as a symbol is completely up to you. Why is 1 minus sine squared cosine squared? Because sine squared plus cosine squared equals 1. You don't even have to justify it for me and write out this identity. But if I subtract sine squared to this side, cos squared would equal 1 minus sine squared. So we can really easily make that substitution from the Pythagorean identity. Okay. Last one I'll do is the last one that's in that note page, number 4. It says cotangent over tangent plus 1 equals cosecant squared. Okay, so from here, we're going to make probably a few substitutions here. I'm going to choose to work on the left side again. It looks like there's just more to work with over here. Cosecant squared is looking a little bare on that side, but cotangent would be cos over sine, right? And then tan would be sine over cos. And when I make those two substitutions, you'll notice that we now have a complex fraction. So there's going to be a couple ways that we work around complex fractions that we'll see in this unit. I would say in this scenario, if you have one fraction divided by another fraction, it might be nice to actually just write this as the top fraction times the reciprocal of the bottom fraction and confirm in your head that that's a legal math move, right? I mean, if I were to multiply the top and bottom by the reciprocal of this, cos over sine, that would be legal mathematics, right? Some of you guys like to say geb foo or something like that. I don't know. But when you're dividing by a fraction, can't you just multiply by its reciprocal? Same thing. So then what do I get? Cos squared over sine squared. Multiplying fractions, you do not need a common denominator. You multiply the tops and then you multiply the bottoms. Okay. Sorry, I'm kind of reaching the end of the page here. Can I extend this further a little bit? All right. So then finally, what is cosine squared over sine squared? Remember what the goal is. We want to try and get this to equal cosecant squared eventually. Well, cosine squared over sine squared is cotangent squared. So I get cotangent squared plus 1. And what is 1 cot? One cot is cozy. Okay, so without writing that last step in there, guys, because I really did just run out of room, that this would be cosecant squared. Okay, that is one of the other Pythagorean identities that we talked about in this lesson. So sorry, that probably was not as quickly as Mrs. Crowfoot could have done it. She's much faster and much more entertaining than I am, but hopefully this helps you to make some sense of what's going on there. The homework's at the bottom of that note page, so give some of those a try and reach out to us and let us know if you have any questions. All right, stay tuned for more identity proofs and equations coming later this week.